All right, so today we're going to be covering all of chapter 25. So this is actually going to be quite a dense lecture. We have to cover all of chapter 25 today since we didn't have lecture yesterday, and during a summer course, we don't really have much time. So tomorrow, the next two lectures will cover chapter 26, so we'll be able to break up chapter 26 a little bit. I'm going to put some more example problems in our chapter 26 lectures, so that you have a little bit more example problems from chapter 25, since today is going to be just a lot of content. Okay, so let's get into it. So today we're going to be doing current, resistance, and EMF. So we're starting our unit on circuits. Now, obviously, I don't have to tell you guys that circuits and electricity make up everything in the world. So we're going to just talk about a couple of examples that I think are the most interesting that maybe you haven't heard of before. So current, what is current? Current is just moving charges. So anytime if we just have a single electron that starts here and he moves over to here, that's a current. Anytime we have a moving charge, that's a current. So in this course, we're going to be studying mostly steady currents. There might be some examples in chapter 26 where we have a variable current that depends on time. But for the most part, we're going to be doing steady currents where we just have, like a 2 amp current or a 3 amp current, and it's not changing with time. So that's what we mean by steady currents. The amount of current is constant with time. Now let's look a little bit more deeply at what is current physically. So if we apply a electric field to a conductor, so I apologize if you guys can hear the lawnmowers outside. My neighbor's doing their lawn right now, so I apologize if that's distracting. Hopefully it won't last too long. So when we apply an electric field to a conductor, now in our previous lectures we said that our electric field inside a conductor is always zero, and that's true for electrostatics when you just have charges distributed on a conductor and there's nothing else acting. There will be no electric field in that conductor. But you can apply an electric field to a conductor. So you can take a wire of copper and apply an electric field through that conductor, and then there will be an electric field and your charges will move according to the force that they feel. It's a little bit unfortunate, we'll talk about this more in a second. When the formalism of electricity and current was developed, they didn't know that electricity was actually carried by electrons. So now we know that electricity is actually negative charges moving through a conductor. Initially, they thought it was positive charges. So our formalism for current is based on the concept of positive charges moving, but it's actually the exact opposite of that in reality. So it's a little bit confusing, but just think when you're thinking of current, we're sort of just doing everything backwards, and we're just looking at it as positive charges instead of physically it's really negative charges moving. So in a conductor, we know that conductors are usually metals, and in circuits, the wires are metal. So let's say we have some wire. There are obviously atoms in that wire that are stationary. So as the electric field is applied to the conductor, the electrons in that conductor are free to move around. And they'll start moving, opposite the electric field. And they're going to bump into each other. They're going to bump into the atoms of the metal. And they're not just going to be able to move super fast down the conductor. They're going to move with what's called a drift velocity. So because these electrons are constantly bumping into things, if they start right here at point P, it sort of bounces around and ends up just a little distance further. So this velocity is actually very small. Even though the electron itself is moving very fast, the rate at which it moves down the wire is actually very slow. And the drift velocity is usually about 10 to the negative 4 meters per second. So that's actually quite slow, even though the electron itself is moving at 10 to the 6 meters per second. That's how many collisions a single electron will encounter as it moves down a conductor. Okay, now let's talk a little bit more, like I said, about the direction of the current. So by convention, we consider current in a circuit the flow of positive charges. So we consider it like this, where the electric field is going to the right and the charges that are moving, the current, is also moving to the right, and they're positive charges, and they're moving at some velocity, the drift velocity v sub d here. Now this, like I said, is actually the opposite of what is physically happening in true conductors like a metal, where the electrons are what are free to move around. And you actually have the case where the current is really made up of the electrons moving in the opposite direction as the electric field. So now all of our physics still stays the same because essentially all you're doing is just introducing a negative sign. The final answer, the final physics of what's happening isn't really changing. So now I'm sure that everyone has heard of Ben Franklin's famous kite experiment where he went out in the middle of a lightning storm, tied a key to a kite, and flew the kite so that he would basically get lightning to strike and prove that lightning was electricity and partially show how electricity works. Now we'll talk more in later lectures about the development of electricity and some other people that were involved in that, but this invention this experiment did lead to the invention of the lightning rod, which we talked about in previous lectures. And now one other interesting thing that I actually just heard about recently is this thing called the Baghdad battery. So in like the 1920s, archaeologists discovered what seems to be a battery in ancient Iraq near Baghdad. And it's basically a clay pot. It has a copper rod inserted into it, and then it's like plugged with asphalt. So if you put vinegar or some sort of electrolyte solution in here, you can actually get a current out of it. And I think actually Mythbusters did an episode on this where they got like a 1 volt potential out of this battery. Now 1 volt isn't really that much, but it's more than 0. So it seems clear that this was some type of battery that was being used 2,000 years ago, which is very interesting because conventionally we don't think that batteries were invented until fairly recently. So this is a very interesting sort of find, and it really kind of makes you question like how much did these ancient civilizations really know about physics that were forgotten or just sort of lost in the course of history and then rediscovered. So this is a very interesting sort of artifact here. All right, now let's get back to what actually is current. So current, the definition of current is that it is the net charge flowing through an area per unit time. So if we have let's say we have a wire here, we're going to look at, let's say we're going to just look at positive charges. So let's say we have some amount of positive charges in this wire. We have some electric field here. Okay. And then we want to look at just a cross-sectional area of this wire. So just take out one slice. So this cross-sectional area is going to, let's just say, have area A. Now these charges we'll say they have charge Q on them. And there's some density of charges in this wire, right? Whatever our metal or whatever material we have, there's going to be some density of charge. So we can define current. If we want to find the net charge flowing through this area per unit time, we can write the current as the density of our charges. So we have the density per meter cubed. Now this number is typically going to be huge, like the order of like 10 to the 28 or something like that. So it's going to be a huge number per meter cubed. So we're going to take the number density of our conductor, and then we're going to multiply it by the charge on each particle. So that's times Q. And then we're going to multiply it by this area A, because we want to find out how many charges are moving through that area. And now we need to multiply by their velocity because we want to know how many are moving through per unit time. So we need to know how fast they're moving. So they're going to be moving through at the drift velocity. So that's going to be VD. And now if we just want to check our units here to make sure that we are getting a charge per unit time, let's just check our units. So the number density, the density of these charged particles is going to be per meter cubed. Let me write it this way because it's just a density. So it's particles per meter cubed. The charge is just coulombs. The area is just meters squared. And then the velocity is meters per second. So if I look at what I have here, I have a meters cubed on the bottom, meters squared, and then another meter. So all those meters will cancel out. And I'm left with just coulombs per second. So I did get the units that I expect for current, which is charge per unit time. So a charge per unit time kind of sounds like a derivative. So we can actually rewrite this as a derivative. And we can write the definition of current as the derivative, the time derivative of charge. And that's the net charge. So I have capital Q here because it's the net charge moving through that area. So this derivative is equivalent to what we just found here. So this is our formal definition of current. Now, a couple of things to note here. The first is that current is not a vector. So you will often actually, see current denoted with a direction, but it's not really a vector. And we'll talk about that more when we get to current density. So as I mentioned, the unit for current is coulombs per second, which is called an amp, which we denote A. And then we have the number density of the charged particles. I took the absolute value here of the charge, and then I also took the magnitude of the drift velocity. So it's just everything's positive here. We never have a negative current. Current is always a positive quantity. So just take the magnitude of everything here. Don't worry about any negative signs yet. Okay, so this formula is very important, especially the fact that current is the time derivative of the total charge. We're going to be using that a lot, especially in chapter 26. So now let's talk about what is a vector. So current is not a vector. Current density is a vector. So current density is denoted by J, and it's basically just the density of current. So it's the current divided by the cross-sectional area of our conductor. So now you'll notice here that I didn't draw a vector on this top equation because current is not a vector and neither is the just the area here. So this is just the magnitude of J. And then if we want to put a vector on it, we can just keep all of our signs in our previous equation. So we can have the number density, then you multiply by the charge of the carrier, so whether they're positive or negative, and then the actual drift velocity of those charges. And that will give you a true vector formula for the current density. But typically, your current density is always in the same direction as your current, so you don't really have to worry about like the vector nature of it that much at this point, since it's always going to be evident what direction it's in. It's not really going to matter too much for our course. But that's just an important thing to keep in mind. Current density is a vector, current is not. We're always going to have the current density in the same direction as the current in this class. So, all right. We'll be doing some examples with this in our next two lectures. Now let's just do an example with this. So we have a wire of diameter 0.98 millimeters. So let's just write that down in our standard units. So the diameter is 0.98 times 10 to the negative 3 meters. And it carries a steady current of 0.26 amps. The free electron density, so that's the number density, the density of our electrons in the conductor, in the wire is 8.5 times 10 to the 28 per meter cubed. So N is equal to 8.5 times 10 to the 28. So that's obviously a huge number. Find the magnitude of the current density and the drift velocity. So our current density we can find using this equation, right? Because our current density is just the current divided by the cross-sectional area. And if we have the current and we have the diameter of the wire, we can easily find its area or the cross-sectional area. So imagine we have a wire like this and its diameter, or, if you look at it like this, its diameter is basically 1 millimeter. So the area of our little wire will just be pi r squared, but r is going to be 1/2 the diameter, so we'll just say the diameter over 2 squared. So J will just be equal to the current divided by pi diameter over 2 squared. So that comes out to, we have 0.26 amps. Then we've got pi, we've got 0.98 times 10 to the negative 3 over 2. And then we square all that. And that number comes out to 3.45 times 10 to the 5 amps per meter squared. So this is our current density. And now we want to find the magnitude of the drift velocity, so the speed. So VD. we can look back at this equation right here. Our current density is just the number density of our particles times their charge times the velocity, the drift velocity. So we can just write that J is equal to NQ VD. And since we're just looking for the speed here, we can ignore all the negative signs because we're just taking the magnitude anyway. So our VD will just be equal to J over NQ. So VD is equal to J, which was 3.45 times 10 to the 5, over N, which was 8.5 times 10 to the 28, and then Q is going to be just the magnitude of an electron charge. So that will just be 1.6 times 10 to the negative 19. So this comes out to, let me just rearrange this a little bit. So this comes out to 2.5 times 10 to the negative 5 meters per second. So that's about what we would expect. We would expect a pretty slow drift velocity on the order of 10 to the negative 4, 10 to the negative 5, something like that. So we're going to do a few more examples that go a little bit more deeply into current density and current tomorrow when we have a little bit more time. But for now, let's go on to resistivity. So at normal everyday temperatures, the electric field inside a conductor and the current density are directly proportional to each other. And this constant of proportionality is called the resistivity. So it basically tells you how strong of an electric field do you need to get a certain current flowing. Another way of saying that is resistivity measures how resistive a material is to current flow. So you can see here, metals have almost no resistivity. This, we've got 10 to the negative 8 here. So that means that if you have a certain electric field, you can get a huge current flowing through that conductor because this number is so small, right? If I have like 10 to the negative 8 here, and let's say I have a electric field that has a magnitude of 1, that means that my current is going to have to be 10 to the 8. So you can get a huge current for your electric field. Now, over here, if we look at these materials that are typically insulators, like glass, quartz, these are absolutely huge. So we're looking at like 10 to the 14, 10 to the 16. So you can see that if you have a resistivity of 10 to the 16, that same electric field is now only going to give you a current of 10 to the negative 16. So materials with high resistivities get very little current for a certain applied electric field. And that's why metals are such good conductors, because you don't have to apply that big of an electric field to get a fairly large current. So now we can take the reciprocal of this, and that's called conductivity. So conductivity measures how easily a current can flow through a material. So conductivity is also given by sigma. So I know that's a little bit confusing that we have a surface charge sigma and now we have conductivity sigma, but we're not going to be using this that much. So it's just 1 over the resistivity. So since conductivity and resistivity have this inverse relationship to each other, so that means for a perfect insulator, now remember an insulator we said the charges are not allowed to move. So in a perfect insulator, if you apply an electric field, none of those charges will move. In a perfect insulator, it has infinite resistance and 0 conductivity because of this reciprocal relationship here. Now, a perfect conductor will ideally let all of the charges move, so it has infinite conductivity and 0 resistance. Now, you might think that these are just sort of limiting cases and we can never get a perfect conductor, but something very interesting happens at low temperatures to certain materials. So the resistivity generally for a material will change with the temperature. So now we're not going to be using this equation in any of our homeworks or exams or anything, but just so that you see it, the resistivity does have a temperature dependence. Now, you can graph this temperature dependence for certain materials, and you can see for a metal, as the temperature increases, the resistivity increases a little bit as well. Now, we're not going to talk about semiconductors too much, but for a semiconductor, the resistivity decreases with increasing temperature. So it's kind of the opposite case as we have with metals. So now in superconductors, you see up here, you have the relationship where your resistivity just increases with increasing temperature. But then when you get to a certain temperature, called the critical temperature, the resistivity drops to 0 and it becomes a perfect conductor. So these are called superconductors. So these were actually discovered in 1911. I think the first superconducting material discovered was mercury. And now when we say low temperatures, they're super low. So the resistivity of mercury drops to 0 at 4.2 degrees Kelvin. Now remember, 0 degrees Kelvin is absolute zero where nothing can move. And 4.2 degrees Kelvin is negative 452 degrees Fahrenheit. So that's obviously extremely cold. So this is the temperature range that superconductors typically work at. So now what can superconductors be used for? Well, one of my favorite uses of superconductors is at particle accelerators. So the largest particle accelerator in the world is at CERN, which is on the border of Switzerland and France. So this accelerator is 27 kilometers long, which is like 15 or 16 miles in diameter. We accelerate particles like protons and ions. We accelerate them to 99.9% the speed of light and then smash them together. Now, to smash something as small as a proton together, you need to keep these particles on a very, very precise track. And that's done using superconducting magnets. So these superconducting magnets have to be kept extremely cold. And they're actually so cold, they're colder than outer space. So the superconducting magnets at CERN are 1.9 degrees Kelvin, which is negative 456 degrees Fahrenheit. And outer space is actually warmer than that by almost a full 2 degrees. So these are the coldest things in the known universe. Maybe if there's like an alien civilization that also has superconductors, it's colder there. But these are the coldest places in the known universe. So these are two pictures of CERN. This is the actual superconducting magnet at CERN. And these are two of my own pictures that I took at Brookhaven National Lab, which is on Long Island. This is smaller than CERN. It's only about 3 kilometers long, but it's still pretty big, obviously. So anyway, so that's one use for superconductors. So now let's move on to resistance. So resistance and resistivity are very closely related. Resistance is dependent also on the shape of our conductor, whereas resistivity is really just dependent on the actual material. So we can write the resistance as the resistivity times the length of our conductor, since we're typically just going to be looking at essentially very thin wires. So the length of our wire divided by the cross-sectional area of that wire. So let's say we have a thin wire. We've got some cross-sectional area A here. And this is some length of wire L we're looking at. So I'm just looking at one little length of the wire here, and we are applying an electric field through it. So there's an electric field, a constant electric field, let's say pointing to the right. Now, if I wanted to figure out what the potential difference between the two ends of my wire were, I could do that actually quite easily, because I know that there's a constant electric field in this wire, and I know the length of the wire. I can say, well, this is equivalent to the problem we did where we found the potential between the two plates of a capacitor. Because for a constant electric field, remember the potential is just the integral of the electric field. If I'm just integrating a constant, it's just going to come out to be E times the length, right? So the difference in potential between this end of my wire and this end, if I have a constant electric field moving through it, is just going to be the electric field times the length. So this end we'll say is at potential EL, and we'll say this end is at 0. So I can write my potential for this little length of wire as E times L. Now, can I rewrite E in terms of the current? Yes, I can, because I know from our previous slide that the electric field is just the resistivity times the current density. So let's rewrite E is rho times the current density, but I can also rewrite the current density in terms of the current because I know that J is I over A. So I can rewrite this as rho times I over A times L. And this is my potential in this length of wire, or my potential difference rather between the two ends. So now from this equation, if I just move I, so if I just move my current over to the other side, divide by I here, I'm left with just the potential divided by the current is equal to rho times the length divided by the area, the cross-sectional area. And this I said is my resistance. So you can think of resistance as the constant of proportionality between the potential in your wire and the current going through it. So this is R. So we can think of the ratio between the potential and the current is equal to the resistance. And I can obviously rewrite this equation as I times R. Now this is a very, very famous equation. So this is called Ohm's law. It's maybe the number 3 most famous equation in all of physics besides E equals mc squared and F equals ma. So Ohm's law is not really a law. It's not true in all cases, but it'll be true in all of the cases we look at. So it's a law, close enough. So Ohm's law just relates the potential through some circuit element to the current going through that element and the resistance of that element. Now I forgot to write here, resistance is measured in ohms. So this is the symbol for ohms. It's a capital Greek letter omega. Okay, so we're going to be using this equation a lot through the next couple chapters. So let's do a simple example. So we have a wire with cross-sectional area of 7.54 times 10 to the negative 7 meters squared. It carries a current of 0.26 amps. And its resistivity, so rho, is 1.72 times 10 to the negative 8 ohm meters. And the units of resistivity, I also forgot to mention, are ohm meters. So now we want to find the magnitude of the electric field in the wire, the potential difference between 2 points 50 meters apart, and the resistance of that length of wire. Okay, so this one's kind of just basically plug and chug, so let's get used to the equations here. So first we want to find the electric field, the magnitude of the electric field. Okay, the magnitude of the electric field I can figure out because I know that the electric field in the wire is going to be the resistivity times the current density, and I know the current and I know the cross-sectional area. So I can figure out the current density, and I'm also given rho. So I can just plug in here rho, the current, and then divide it by the cross-sectional area. So rho is 1.72 times 10 to the negative 8. The current is 0.26 amps, and the cross-sectional area we're given is 7.54 times 10 to the negative 7. So just plug all that into your calculator and you get 0.00593 volts per meter. So this is the magnitude of our electric field. Okay, so that was relatively straightforward. Now we want to find the potential difference between 2 points in the wire that are 50 meters apart. So we can use the equation that we just previously had, where the potential between 2 points in our wire with a constant electric field will just be the electric field times the distance between those 2 points. So all we have to do here is just multiply our electric field by the distance between those 2 points, which is 50 meters. So we just have to multiply that, and we get 0.297 volts. So that is the potential difference between 2 points 50 meters apart. And now we want to find the resistance of that length of wire. So the resistance is going to be rho times L over A. And this, rho, we have everything we need again. So rho we have is 1.72 times 10 to the negative 8. The length we're looking at is 50 meters, and the cross-sectional area we have as 7.54 times 10 to the negative 7. Okay, and this number comes out to 1.14 ohms. So 1.14 ohms is our resistance. Now, in most of our problems, we are going to be using the resistance and not the resistivity. As I said before, since the resistance depends on the shape of your whatever circuit element you're looking at, we're typically going to be looking at like a fixed circuit element that has a definite shape. So it's more convenient to use the resistance versus the resistivity, which is geared more towards just the material in general. All right, so now let's talk about circuits. So in our previous examples, what we've been doing is we have some length of wire and we have charges moving down it. So we'll have electrons, let's say, moving in this direction if we apply an electric field. Now, if we just have a finite length of wire that's just ends at either end, well, what's going to happen when the electrons get to this end? Are they all just going to pile up right here? And then where are the electrons coming from? Is there like some infinite source of electrons at this end that makes the electrons keep moving down the wire? No. So what we need is a complete circuit. We need a closed loop so that these electrons can move in a continuous path. So we're going to have a closed wire loop like this. We'll typically have a battery somewhere, which we denote by two lines like this, where one is longer than the other. And this battery will supply some potential to my circuit, because you can imagine as my electron moves around the circuit, it's going to lose energy. So it decreases its potential energy. It needs something to lift it back up so that it can keep circling this circuit. Just like if you go on a roller coaster, the track is a closed loop, but at some point you need to go up in order to come down. So it's the same idea. The battery just provides power to keep the charges flowing in our closed circuit. In a closed circuit, a wire loop is called a complete circuit. So let's talk more about this potential that the battery supplies. So we know that for an electric field, the potential around a closed loop is zero, right? We said that the potential around any closed loop will be zero since the electrostatic force is a conservative force. So that means that when you have your electrons that start here, they go around your circuit, they're going to be back at zero potential once they come back around. So like I said, we need something to keep the current moving, and that is a source of EMF. So EMF stands for electromotive force. Now, it's not really a great name because it's not really a force. You're supplying a potential difference. It's not really a force in the traditional sense. But again, they came up with a name before we knew really what it was. So we have an unfortunate name attached to EMF. So it's written with the symbol for EMF is this like fancy E. And the EMF just supplies some potential difference to get the electrons back up that potential hill so that they can roll back down around the circuit. Now, an ideal source of EMF is equal to the potential difference supplied by that source. Now, this doesn't happen in real life. We don't have ideal batteries. So in a physical battery, a little bit of energy is lost in the battery itself, because since we don't have superconducting batteries in everyday life, there's a little bit of resistance in the battery itself, and some of that energy, some of that potential difference is lost to that internal resistance. So this is called internal resistance of a battery, and we write it as a small r. So we have the potential difference through, let's say, the two ends of a battery are equal to the EMF supplied by that battery, which will be in volts. And then you subtract the potential difference, or the potential that's lost, to that internal resistance. So that's minus the current times the small resistance, the small internal resistance of your battery. So let's look at this a little bit more carefully now. So we said that the electric force is conservative when we have a static electric field. In this case, we do. Even though the charges are moving, the electric field is static. It's just some constant value. So we know that the potential difference around a closed loop in a complete circuit must be zero because the force is conservative. So we can write this as essentially a conservation law. So we have the EMF of the battery minus the internal resistance of that battery, the energy lost or the potential difference lost in that battery, minus the potential difference or the potential drops as you go through the circuit, and that will all be equal to 0. So now let's look at this diagram a little more carefully to understand what's happening. So we have here a 12-volt battery that has some small internal resistance of 2 ohms. So this is how it's drawn. Typically, you have the battery here. This is the positive terminal. Then the internal resistance is here, and it's all encased in like, what looks like a little battery. These wires here that make up your circuit, we consider the wires that connect the elements of our circuit to have 0 resistance. So these are perfect conductors, you can imagine. And now resistors are where we lose energy. So for example, your toaster, the coils in your toaster are very high resistance. So when you send a current through them, they get really hot and they dissipate energy. So you lose energy when you go through a resistor. So, okay, we have a little particle here. It starts out at 0 potential, just like the roller coaster analogy. The EMF of the battery shoots it up to the top where it has a potential of now 12 volts, the EMF of the battery. The battery, as the particle moves through the battery, it loses a little bit of that potential difference due to the internal resistance of the battery, so it loses a little bit of energy. So it falls down an amount, current I times R, so the current in the wire times the internal resistance of the battery. So it loses a little bit of energy here. Nothing happens as it goes along this wire because it's a perfect conductor. It gets to this resistor, loses more energy equal to an amount current times resistance. So the current in the wire is 2 amps. The resistance is 4 ohms of this resistor. So we get a potential drop of 8 volts. And then it continues around the circuit here, and we're back at 0. So that's how you can think of these circuits. So now let's just go over, before we do more circuit stuff, let's just go over the parts of a circuit. So you'll see a voltmeter. If you had an in-person lab, you would actually be using voltmeters, but we don't. So a voltmeter just measures the potential difference between 2 points. So a voltmeter will be drawn like this on your circuit, and it will have like points A and B measured or labeled, and it will just tell you the potential difference between point A and point B. So it will tell you VA minus VB. Now, an ammeter is over here, and an ammeter measures the current through your wire. And then we have these other elements here. So a straight line is just a wire with perfect conductivity. It has no resistance. This little jagged red thing is a resistor. So you'll lose energy, you'll lose potential difference there. This represents a battery, these 2 lines. This here, as we just saw, represents a battery with internal resistance. And you can draw it either way. And then voltmeter and ammeter again. And then we'll also see next time, this is a capacitor. So when you have these 2 lines that are equal length, that will denote a capacitor in our circuit. But we'll see that in our next lecture. All right, so I mentioned that as you go over a resistor, your circuit is going to lose energy. You're going to dissipate energy or power through that circuit element. So power is just the energy transfer per unit time. So power is just the energy transfer per unit time. It's the rate at which energy is transferred, and it's measured in watts, which are joules per second. So it's energy per second. Now you can write power in a couple of different ways. They're all equivalent, obviously. So power first is the current times the voltage drop across that element. So in the example of a resistor, the current through the resistor is 2 amps here. And then you would have to figure out, well, what's the voltage here and what's the voltage here? And that voltage difference you'll multiply by your current, and that will give you the power dissipated through this resistor. So we're obviously going to be doing examples with that. So that's how you would find the power dissipated, the energy per second dissipated through that resistor. Now, you can also, by using this equation, by using Ohm's law, you can get these other forms of power. And like I said, they're all the same. Now we can also rewrite power as the EMF from our source. So we said that the voltage in a non-ideal battery is given by the EMF minus the current through the battery times the internal resistance of the battery. So if you just replace the V in our P equals IV equation with this fancy E minus IR, we get this equation. So this is the power that's dissipated within the source. And that's this little negative term here. So this is the power that's lost in our battery, and this is the power that the battery supplies. The positive term is power that the battery supplies. The negative term is the little bit of power that's lost to the internal resistance. Now let's do some examples using this. So we have, for the circuit shown, what are the voltmeter and ammeter readings? So we want to figure out what's the potential difference between point A and point B, and then what's the current going through A. Okay, so here we have a battery with an internal resistance of 2 ohms, an EMF of 12 volts, and then we have another resistor over here of 4 ohms. So let's first find the current. So let's write what's essentially our conservation of energy equation. So this is the potential difference, basically as we go from one terminal of the battery to the other. We have the positive potential supplied by the battery, and then we lose the little bit in the internal resistance of the battery. And this V will be equal to, we can use Ohm's law to rewrite V. So that's the potential drop across the resistor. So now this I and this I are the same because we just have one steady current going through the circuit. So we can actually use this equation to solve for I first, and we can figure out what the current is, and that will be the ammeter reading. Now, the ammeter reading is just saying what is the current. So let's solve for I. So I can rewrite IR. I'll move the little IR to the other side. And now I can factor out an I. I have capital R plus little r. And then I can divide both sides by capital R plus little r, and I get this equation. So now I have everything here, right? I have my EMF supplied by the battery is 12 volts. I have the capital R, which is the external resistance, the resistance of that external resistor here. And then I have the internal resistance of the battery. So just plug those things in. So we get 12 divided by, we have 4 plus 2. So that's obviously 12 over 6, which is 2. So our current is 2 amps. So that's our current that's moving through this circuit. Now we want to find what is the voltmeter reading. So what's the potential difference between this point and this point? So you can look at that two ways. You can say if I have a particle, or if I look at a particle that moves from point A through this wire, passes through this resistance here, it's going to have a voltage drop as it goes through this resistor, and then it moves to point B. What's that voltage drop that it experiences across the resistor, since that's the only drop in potential it experiences? So you can do it that way and say, okay, that will be V equals IR. So it's just the current through the resistor times the resistance of the resistor, which is just 8 volts. And that's our answer then. Just has a potential difference of 8 volts here. Or you can look at it, like essentially this side of the equation and say, okay, well, as it gets moved up that potential hill by the battery, how much potential is the battery supplying? And you can look at it this way. You can say it's the EMF minus the current through the circuit times the internal resistance, and you'll get the same answer. 12 minus the current is 2, and the internal resistance is 2. So it's just 12 minus 4 is 8. So either way, you get 8 volts. And you might say, like, well, how do you know if it's positive or negative? Since I was a little careless with, VA minus VB versus BV minus VA. But basically, it's because you know over here, so this is the positive terminal of your battery. That's going to be like the top of your positive, the top of your potential hill. So you know as soon as a particle goes past the positive terminal of its battery, it's been moved up to the top of that potential hill. It's been moved up here. So I know that my potential is higher over here than over here. But since we know that the total potential across the whole circuit has to be 0, as long as you know that it's higher over here than over here, it doesn't matter which way you calculate it. You know that your answer has to be positive either way. All right, now for this next example, we're looking at the same circuit, but now we're looking at the power. So we want to find the rate of energy conversion, chemical to electrical, energy dissipation in the battery's net power output, and the rate of energy dissipation in the 4 ohm resistor. Okay, so there's a couple terms here that we should just go through. So we're going to be using this equation since we're looking at the power in a battery. So when they say the rate of energy conversion, that's this first term here. So that just means how much energy is the battery basically turning from chemical potential energy to electrical energy. So that energy conversion is just going to be the current through the battery, which is 2, times the EMF supplied by the battery. So that is 12. So that gives us 24 watts. And now, when they say the energy dissipation in the battery, so let's call that P1 and P2 maybe. Okay, then the rate of energy dissipation in the battery, that's saying how much energy is being lost per second in the battery itself to that internal resistance. So that, as we said, is just this second negative term here. So that will just be, we'll just look at the magnitude, I squared little r, which is just I squared, so it's 2 squared times the resistance in that battery, the internal resistance. So this is going to be 2 times 2 times 2, which is 8. So we've got 8 watts is lost within the battery itself. And now the battery's net power output. So the battery's net power output will be this whole thing. So it will be this minus this. So P net, we'll say, is that 24 watts minus 8. So the battery itself can convert 24 watts of chemical potential energy to electrical energy, but it loses 8 of those because it has some amount of internal resistance. So once you're out of the battery, essentially, what you see is this 16 watts of power output. And now we want to know, well, what's the rate of energy dissipation in the 4 ohm resistor? So you can kind of guess what it's going to be already if you think about conservation of energy, but we can also double check. So in this resistor, we can use one of our equations for power through a circuit element was I squared times R. So here, the current through our resistor is 2 amps, so it's 2 squared times the resistance of the resistor, which is 4 ohms. So this gives us 2 times 2, which is 4, times 4, which is 16. So we've got 16 watts. And now I say you could sort of guess this is because if you know that the potential around the entire circuit is 0, that means that whatever energy you create over here in the battery is going to be lost somewhere by the time you get back to the starting point here. So the net power output of your battery is 16 watts. So that puts power into or energy into your circuit, and then your resistor dissipates it, and you get back to 0 at the other end of the battery. Now let's look at the same circuit again, but we replace the 4 ohm resistor with an 8 ohm resistor. So we're replacing this guy over here with an 8 ohm resistor. How does the power dissipated in that resistor change? Now you might say, okay, well, I'm going to do the same thing again. And you'll get the current is 2 squared times 8. So that's 4 times 8. So that will be 32 watts, right? Yeah. So you might look at that and say, okay, that's my answer. But would that really make physical sense? It would not. And the reason that is that if you think about it and you say, okay, well, my battery was outputting 16 watts of power. So how could my resistor dissipate 32 watts? Where did that other 16 watts come from? Well, that doesn't make physical sense, right? That energy, you can't just create energy out of nowhere. So that's an indication that your answer is not correct. And the reason that this isn't correct is because if you increase the resistance of this resistor, you actually change the current that's in your entire circuit. So we have to find the new current first before we can figure out the power. So let's figure out the new currents. We can do it exactly the same way we did previously, where we write V is equal to E minus I little r. This is capital IR. And then we will solve for I the same way. You end up with the same equation here. So now we have our EMF is the same, it's still 12 volts. Our capital R, so the resistance of this resistor over here, has now increased to 8. So we have 8, and then our small r, the internal resistance, is still 2. So we get 12 over 10, which is 1.2. So our new current has decreased. Our current now is 1.2 amps. And that's basically because if you increase the resistance along your circuit, so it's harder for charge to flow through this circuit now because we increase the resistance. So it makes sense that our current should decrease because less charge can get through. It's harder for charge to move around our circuit now. So the current decreased. So now we can figure out how much power was dissipated through this resistor. So we can just do the same P equals I squared capital R. So we just do I is 1.2 squared. The resistance of that big resistor is 8. And this comes out to 12 watts. Now let's just check our total power that's supplied by the battery to make sure things make sense. So we did the total power from the battery is I EMF minus I squared internal resistance. So the current was 1.2 times 12 minus I squared now is 1.2 squared times the internal resistance, which is 2. So this comes out to, technically, it's 11.52 watts, which I should have not rounded. 11.52 watts here and 11.52 watts there, or 11.5, whatever you want. Okay, so our power is the same as we would physically expect. So always make sure you do sort of sanity checks on your work, especially as you're doing these problems where it's very easy to make a mistake in these. Okay, so that's all our problems for today. In our next lectures, we'll do chapter 26, and we'll do a lot more examples, since I personally think chapter 25 and 26 are the hardest in the class, at least like conceptual wise. So we'll make sure we do a lot of examples for these couple chapters. Okay, and I will see you guys next time.